Hello, we are Team 6 of the UAS SAR course, and this is our final presentation on our project and the lessons we learned. First, I'll be telling you a quick rundown of the base knowledge required to understand our work in this class.
Next, I'll present the basis of our project, how we designed the system to communicate and interact with the simulated radar.
I'll then explain the post-processing step of back projection, where we turn incomprehensible numbers into images.
Finally, I will tell you about the next steps and extra projects that we took on.
So, what was this course all about? Here's what we learned in a month, condensed to around 30 seconds. Radar is a way of detection that sends and receives radio waves to detect objects, and even though you can't see it, radar can be used in everything from collision detection on cars to winning world wars. So, how exactly does radar find a distance to an object? It transmits an electromagnetic wave which hits a target, and part of the radar echo is then reflected back to the radar antenna. The difference in time, tau, between when the signal is sent and received is proportional to r, the distance to the object. There are many different modes of radars that all specialize in specific functions, and this course dealt specifically with synthetic aperture radar. SAR is used for surface-level imaging to detect and classify stationary targets, and the positives of radar are at play in comparing these images of Venus. The SAR image is unaffected by weather, unlike optical imaging, so it provides a clear image of the surface.
Moving on from radar basics, let's talk about how we control the radar. We have to be able to interact with and get data from the radar and prepare it for post-processing to generate an image. The technique we use for generating the image is called back projection, which we will elaborate on later. On this slide, we see a diagram of how the radar host will communicate with the radar. First, we establish communications and make sure the radar is running with a comm check. Once communications have been established, the host will initialize settings of the radar with set and get configs. Then the radar host tells the radar how many scans to take and will start receiving data that the radar sends back. And after the radar finishes scanning, the host reads the formatted data and generates an image from it. In our implementation, we also reboot the radar and radar host to reset the data collected so we can collect more data after the radar finishes its scans. To make it easier to control the radar, we create a GUI, or graphical user interface, that acts as a remote control that allows us to run each of these steps separately.
So now that we can reliably get data from the radar, we need some way to turn that jumble of numerical data into some recognizable image, and that's where back projection comes in. Back projection is a post-processing technique which efficiently generates high-resolution SAR images. It's an algorithm which calculates reflectivity or brightness of the data returned from each pixel. The algorithm we applied to back project followed these basic steps. We first correlated coordinates of the data to pixels so that we can pick a center point and where we will start generating. Next, using the formula, we calculated reflectivity. Then we interpolated the scan data, which made our image pixels more precise, and then finally repeated this for each pixel, making up the image. Although this process can create really high resolution SAR images, a big caveat with back projection is that it's very time consuming and tedious, as it generates an image by going one pixel at a time. We accounted for this by overall streamlining our code and removing any unnecessary functions and replacing and reducing our number of for loops to significantly increase our back projection speed, in one case from about 30 seconds to 9 seconds for one image. So just for a little demo, on the left, we can see the plotted scan data that we have, which we back projected to see this image on the right. If you could take a guess, it's the MIT letters.
We also had some extra projects to take on outside of command and control and back projection. Although the bulk of our time was spent on these main portions of code, we pursued extra projects to test the capabilities of our radar. We combined our newfound knowledge of radar with machine learning and Python fundamentals to attempt to create a vehicle detection system. We also explored creating a radar GUI and features like continuous scanning and a progress bar to give the user a better experience. In one of our classes, we discussed how machine learning is being used to classify objects in radar images, and later, the vehicle detection project was offered. We researched what object detection is, and we used the TensorFlow Python API to attempt to create our own model. Our main problem were the incompatibilities with our machines, so instead, we used the Python OpenCV libraries and an already created object detection model. We created training data through the Darknet repository. Although we were unable to form sufficient models with our data due to time and data constraints, we still learned about the role object detection plays in SAR imaging. As talked about before, the radar GUI is an easier way to set and confirm all of the parameters for the radar, including how long the radar is scanning for, how many scans to take, and when to plot or back project the data. Continuous scanning was a function we were able to implement by following the radar's API and controlling the data intake through a keyboard interrupt, and later data manipulation. The progress bar, inspired by our instructor's code, was an added feature to give the user an ETA and animation to show how long back projection was taking.
Here's some of our key takeaways from the past 4 weeks. I found that when working on a problem, it's good to consider multiple approaches to the same problem before sticking to one. A lot of the time, the first idea you have is not the best.
I learned that it's really important to test everything, especially when you're writing a very long, complex code, because you want to be able to find the root of the problem by testing things individually.
I learned that code optimization is necessary to efficiently test other facets of your project, especially with so many moving parts in a complex project.
And I found that working through and pre-planning your code beforehand and just working through the logic step by step is really helpful in building a really complex project.
Finally, I'd like to say thanks to our entire team, the UAS SAR students and staff, especially Ramu, Frank, Mason, Rima, and Winston. Special thanks to Bob Shin and all of the BWSI staff for hosting such an amazing program. Thank you.